In this video, we will be starting Chapter 3. Chapter 3 is stoichiometry, which is a fancy way to say that we are going to be writing out equations and doing mole calculations based upon those equations. So what we'll eventually be doing by the end of the chapter is we might have a reaction. So it might say that we have propane and it undergoes combustion. And they might tell you that you start with 25 grams of propane, 25 grams of oxygen. Then you'd be asked to determine how much of each product was produced and how much of the excess reactant remained. So there's some skills that we need to work on in order to get to that point. We need to be able to write out the equations for the chemical reactions. We need to be able to do mole calculations. And then we also, if we're given two reactants, we need to figure out which one is the limiting reactant, which one gets consumed first. So we will be acquiring each one of those skills and then eventually putting them together at the end of the chapter. So first we have just a little bit of review about our chemical equations just to refresh our memories. So a chemical change is a change that involves the reorganization of the atoms, and it will end up producing new substances. If we take a look at the particle diagrams, you'll see the atoms rearranging, or from the equation, you can see that we started with ethanol and oxygen gas, and then we produced two new products, carbon dioxide and water. So this is a chemical change because we formed new substances and the atoms rearranged. We have different things connected to different things. So bonds were broken, bonds were formed. Now, one thing you might also remember from Regents chemistry is doing problems where we talked about it being like a recipe. So the balanced equation gives us the ratio, the mole ratio of how they have to react. So 1 mole of ethanol reacts with 3 moles of oxygen to produce 2 moles of carbon dioxide and 3 moles of water. So that gives us our mole ratios. Now, just like a recipe, we can make changes to our recipe or our reaction. We can double it. So now if we were reacting 2 moles of ethanol, we would need 6 moles of oxygen. That would produce 4 moles of carbon dioxide and 6 moles of water. So we have the same reaction that we had on the previous slide. We just have 2 quick examples to do with them. So if 3 moles of ethanol, so here's the ethanol, there was no coefficient in front of it, so that would be like a 1. We are changing that to 3. So we are tripling the amounts. It asks how many moles of water would be produced. So normally when you reacted 1 mole of ethanol, you produced 3 moles of water. Well, if you're tripling your recipe and reacting 3 moles of ethanol, you would produce 9 moles of water. Now you also could have looked at their ratio. They're in a 1-to-3 ratio, so 3 to 9 would be the same thing. You could also set up a proportion if the numbers were less easy to work with, such as this next example. So we have 0.015 moles of oxygen. So now we're looking at the O2 are consumed. How many moles of carbon dioxide was produced? So it's a little difficult to be like, okay, we're going from 3 to 0.015 off the top of our head. And you're a 3-to-2 ratio, so you could do it that way. To maintain the 3-to-2 ratio, you could figure out how many moles of carbon dioxide, or you can use dimensional analysis, one of my favorite skills. So we take what we're given, we put that over 1. We know that moles of O2 need to go in the denominator so that it cancels. So this is going to be a 3 because that's what we got in the balanced equation. The top would be 2 because the 2 in front of the CO2. So it's 2 moles of CO2 per every 3 moles of O2. Then we just do our math and get our answer. So we would divide or multiply by 2 and then divide by 3. So that would give us 0.01 moles of CO2 because the oxygen would cancel. Again, you could have set up a proportion if you find that easier. All right, balancing equations. So we obviously need to have our equations balanced so that we are adhering to the law of conservation of mass, so that we'll have the same number of each type of atom on each side of the equation. So we have to have the equal amount of sodiums, equal amount of hydrogens, equal amount of oxygens. Now, if you are good at balancing, you can try to do them in your head. If you can do them in your head, great. If you want to write them out, that is also great. If you come across one that's a little bit longer or a little bit trickier, you can always feel free to write them out. What I mean by writing them out is just what I am doing right now, which is taking an inventory of what I have if all of the coefficients were 1. So you just count up what you're working with so that you know where your problems are. Normally, I would tell you to hold off on hydrogen because it shows up in more than one spot on the product side, so that just makes it a little trickier to work with. Unfortunately, hydrogen is the only thing that is unbalanced right now, so we have to start with hydrogen. Now, we do not necessarily need to change both coefficients. We may only need to do one. So this is a little bit of trial and error, but if you think about it, this one here is going to be problematic because H2O, it exists as water, you are always going to have an even number of hydrogens on the reactant side. So this one is going to be something that we're going to need to change. So if we put 2 in front of sodium hydroxide, that changes that to 2. It changes O to 2. It changes just those hydrogens to 2, giving us 4. So this almost looks like we made things worse at the moment, but we didn't. If you put a 2 in front of water, that would give us 4 H's, 2 O's, so we're starting to see that we're on the right track, and then just a 2 in front of the sodium would then have us be balanced. So our coefficients would be 2, 2, 2, 1. And that gives us the mole ratio of how they react. Pause the video and balance number 2. All right, so your coefficients would be 1, 3, 2, 2. The way that I started this was I worked with the hydrogen. I knew I had 4 over here, so therefore I needed the 2 in front of the water. And then I also, because I had a 2 there, I needed the 2 in front of carbon dioxide. Then that gave me 6 oxygen atoms total on the product side. Therefore, I needed the 3 in front of the O2. All right, another thing that should be a review is our different types of reactions. So we have a combination or a synthesis reaction. So that's where we have multiple reactants joined together to make one. So H2 plus O2 come together to make water. So they join together to make one product. Decomposition is the reverse of that. In decomposition, you will start with one reactant. So let's say we have aluminum oxide, and then that breaks apart into multiple parts, into simpler pieces. So that would make aluminum and oxygen gas, and then this obviously would need to be balanced. So we'll fix our coefficients there. All right, combustion. Combustion, we briefly talked about when we did organic chemistry. And combustion, you should think exothermic. You should think that it's releasing heat, and that's true. All all combustion reactions are exothermic. Combustion also uses oxygen gas as a reactant, so that's something we need to be familiar with. When organic material combusts, so organic means that it's carbon-based. So if we have a carbon-based molecule that undergoes combustion, so it reacts with oxygen, it will form carbon dioxide and water. So if we get a question that says, write the combustion for methane, they would tell you what methane is, so CH4, so they would give you that, but then they would expect you to know everything else. So if it's combustion, you know it's got to react with O2, and you know that it produces carbon dioxide and water, and then also some heat since it's a combustion. And then we would need to balance it, so we have to put a 2 in front of the water and a 2 in front of the O2. So combustion of an organic material always produces carbon dioxide and water. If we have an inorganic substance, so not carbon-based, it will form an oxide of whatever combusted. And we'll look at an example in a second. All right, so we have our two reactions here. So write out the reaction for the combustion of lead. So we know that lead is Pb because we memorized our elements. We know if it's combustion, it's reacting with oxygen gas. Now, organic combustion produces carbon dioxide and water. But lead is obviously not organic. It is not carbon-based. We also can't produce carbon dioxide or water because we don't have the correct elements. So then, this was our last bullet on the previous slide. It produces an oxide of the thing that combusted. So lead combusted, so we make lead oxide. Now, they were specific because lead can make a +2 or a +4 charge. Since they said that, we know it's lead +2, and we know oxygen is -2, so it would be PbO. If it was the lead +4, then the ratio would be different. If they hadn't specified that, then technically you could answer it either way. Obviously, we still need to balance the equation. So we would put a 2 there and a 2 there, then we would be good. Okay, our second example, we are doing the combustion. So again, we're going to be reacting it with oxygen of ethane. Ethane is C2H6. They would give you that. You wouldn't need to know that. It's undergoing combustion, so it must react with oxygen gas. And since this is organic, we are making carbon dioxide and water. And then ethane is a gas, so we put that in, and you wouldn't need to know that. Then we would just need to balance. Since we have 2 carbons, we'll need a 2 in front of the CO2. Since we have 6 hydrogens, we will need a 3 in front of the water. Then that would give us 7 O's. So we could do 3.5 in front of the O2, and that would be okay. In regions, we always had to balance using whole number coefficients, but you don't actually have to in AP. If you want to do zero point 0.5, that's fine. Alternately, you could have done 2, 7, 4, 6, and that would be perfectly correct.